In this video, we talk about the Gauss and Weingarten maps and normal and geodesic curvatures. In the last video, we talked about how the the curvature of the surface can be quantified. The way the standard unit normal varies clearly reflects the way in which the surface curves. So the values of all the unit normals at the points of the surface are recorded, and we call that we call that as a Gauss map. So this is the map from the surface S, taking all the standard unit normals from the surface S and representing them on the surface of the unit sphere. So that assigns a point on the unit sphere. So it's a map from the standard unit normal to the points on the unit sphere. That map is called as Gauss map. The rate at which the unit normal varies across S is measured by the derivative of the Gauss map. The Gauss map derivative of G is a linear map from the tangent plane of the surface S to the tangent plane on the unit sphere. So it is it's a map from tangent plane to tangent plane. So let P be a point on the surface of S. The Weingarten map is given by the negative of the derivative of the Gauss map. This is the definition for Weingarten map. So let P be a point on the surface. So let define sigma be a surface patch. It is defined through two parameters, u comma v, with P in its image. So let L du square 2m du dv and dv square be the second fundamental form of the sigma. So the Weingarten map, the second fundamental form is defined through this quantity. So the v and w are the vectors on the tangent plane. So the Weingarten map of the v and taking the second fundamental form at the point P on the surface S is defined like this, with the quantities L, M and N. So these L, M and N we defined in the earlier definition, and one can prove that L, M and N can be obtained from deriving from the standard unit normal and the surface patch sigmas. So one can show the equation 45. If gamma is a unit speed curve on the oriented surface, then gamma dot is a unit vector. By a definition, it's a tangent vector to the surface. Gamma dot is perpendicular to the unit normal on the surface. So gamma dot n and n cross gamma dot, they form three orthogonal. They are all orthogonal to each other. They form mutually perpendicular unit vectors. So again, gamma dot is perpendicular to gamma dot. So the gamma dot can be written as linear combination of the standard unit normal and standard unit normal cross gamma dot. The coefficients attached with the standard unit normal is called as normal curvature. The coefficient attached with standard unit normal cross gamma dot is geodesic curvature. So there is a theorem regarding this, that let be a point on the surface yes, v be the unit vector to the surface yes at the point P. Let pi theta be the plane containing the line passing through P parallel to V, the unit tangent vector, that is making an angle theta with the tangent plane on the surface. Assume that pi of theta is not parallel to, it is making an angle theta. Suppose that pi theta intersects the surface along a curve with a curvature, so intersects the surface through a curve with the curvature k theta, then k theta sin theta is independent of theta. This is the theorem. So here it's a pictorial point of view. We have the surface S, P is the point, and we have the unit tangent vector at that point P, and we consider plane making an angle theta with the uh, tangent plane, and it intersects the curve here dotted. It is given this curve has the curvature k theta, and this k theta when multiplied with the sin theta of this angle is independent of the any angle you make. That's the theorem. Thank you.